nanohub.org.
Online simulation, and more for nanotechnology.
All right, welcome everybody to our seminar series today for the Micro Nanotechnology Education Center. Today, Neda Habibi from Northwest Vista College in San Antonio is going to give us a presentation on nanotechnology workshops that they're going to be providing at Northwest Vista College. So thanks, Neda, and take it away.
Thank you, Jared. So I'm just going to start and introduce myself. I'm Neda Habibi. I work at Northwest Vista College. This is a two-year community college located in the city of San Antonio in Texas. I'm the program coordinator of a nanotechnology program at NBC. I'm also the PI of an AT project. It's called Alamo Institute for Materials Technology, the AIMTech project. And also with the Micro Nanotechnology Education Center, I'm collaborating as co-PI. So the Advanced Materials Technology or Nanotechnology program at MVC, this is a two-year degree program. We offer Associate of Applied Science degree in nanotechnology, and we also have two level 1 certificates in nanobiotechnology and semiconductor technology. So the certificates, they have nano courses, engineering courses, and students can complete them in a minimum of 1 year and followed by an internship training. The associate degree, it can be completed in 2 years, and we have like math courses, chemistry courses, as well as nano courses. We do have a nanotechnology lab at MVC. Just briefly talking, we have a variety of instrumentation. We have AFM, SCM, we have XRD, laser cutter, we have a furnace, we have a fume hood. So we have a lot of instrumentation from synthesizing particles to characterizing them. And we have purchased this instrumentation through different grants. One of them is the AT grant that we have. A lot of the instruments were purchased through Texas Workforce Grant, which is actually a grant that is meant to be for workforce programs. And also a lot of instrumentation were purchased through Perkins funding, which is a state funding program. As long as we are benefiting students' education, there's a limitation each year that we can purchase instrumentation. We are also keeping some of our instrumentation at Southwest Research Institute. SWERI is actually an industry collaborator that is working with us. They are keeping some of our instrumentation in their lab. They have several departments like Department of Materials, Department of Biomedical Engineering, and they provide service like research service to their customers, which is mostly industry. And both parties are benefiting here. Our students can go there and work with the instrumentation and also have an internship experience as well. In this two picture, you're seeing Marisa, one of our students is working in the cell culture lab at SWERI. And Paul, one of our students is working with the field emission scanning electron microscopy at UTSA. So a little about myself. I have a PhD specializing in nanobiotechnology from University of Geneva, Italy. I graduated in 2013, and since then I spent 8 years in academia doing research and teaching. The last 4 years I've been in US. In 2016, I joined UTSA as a research fellow and assistant professor of research. And from 2017 until now, I've been the program coordinator of this nanotechnology workforce program at NBC. So this program is focused on materials engineering and nanotechnology. Material science is a major that in 1970s and 1980s, it wasn't recognized as a distinct major, and it was more like a subfield to other majors like chemistry and physics. And the classical field of materials engineering, it was focused on studying solid state and bulk structure like metals, ceramics, and other polymers, and kind of studying how the processing of these materials are affecting the properties. But in the recent years, with the progress of advanced technologies, especially macro and nanotechnologies, material science has been revolutionized in terms of now we can work with materials in the atomic level to create new and modern devices. So whatever material science has achieved so far, the future of this science is going to be focused on how we can use micro and nanotechnologies to actually create new structures and modern devices that have enhanced properties compared to their conventional structures. So according to many scientists, the future science is going to be focused on micro and nanotechnologies, cybersecurity, and also artificial intelligence. So I think it's important for us to give students the background knowledge and the set of skills of this modern technology. So this program is focused on different areas. First of all, we teach students how to synthesize nanoparticles. We can do this in different ways. For example, the wet chemical synthesis approach, which is used to synthesize nanoparticles that are suspended in a solution. The atomic layer deposition, which is used to make thin films. And then we want to characterize these nanostructures using different instrumentation like SEM, AFM, FTIR, and so on. And finally, we want to use this knowledge to be able to create new materials. So we want to apply those nanoparticles in creating new structures. Before starting any kind of lab work, I always like to review lab safety protocols, even if we're not doing a dangerous experiment, even if we're not working with hazardous chemicals. I like to review lab safety protocols, and I think it's important. I start by introducing the materials data safety sheets. So I ask students for whatever chemical structure that they want to use in this experiment, they go and do a search and find the MSDS sheet. And this is a very good approach to kind of have a quick review. What is the health hazard of this reagent? What is the specific hazard? Is it corrosive? Is it bad for inhalation? And students can have a quick review and know how to handle these chemical reagents. I also like to introduce the hazard labels like a fire hazard, corrosive hazards, and so on. And also introducing the diamond hazard, which you can see in this picture. The diamond hazard has 4 areas. The white part, which is a specific hazard. If a reagent is oxidizer, you see an OX symbol. If it's acid, you see an acid symbol. And the blue part is the health hazard. If you cannot read it, I will read. It's ranked from 0 to 4. 0 is completely normal, 4 is deadly. The fire hazard, again, is ranked from 0 to 4. And 0 will not burn, 4 is flammable below 70 degrees of Fahrenheit. And also reactivity is ranked from 0 to 4. 0 is stable, 4 is highly reactive. And we also have the white part. So I always ask students for whatever reagents that they are supposed to work with, they can, these labels are available printed. They can just find the numbers from a web search and put the numbers in this specific area, put the correct numbers, and label all of their bottles so they know how to handle each bottle. Just to give you an example of handling reagents, in sodium borohydride is a reagent that I use in some of my experiments, is a reducing agent. Once this reagent is in contact with water, it will produce hydrogen, and hydrogen is flammable. So of course, when you're using in a very small concentration and diluted form, it's less likely to produce any kind of problems, but I always like students to know how to handle these kind of reagents. And what I tell them is that to make this reagent in small concentration, in diluted form, put the cap on so we're not allowing hydrogen to escape. And also we are discarding the solution the same day, so we don't want to keep a solution that could be potentially flammable. So I always like to review the list of highly hazardous chemicals, and the top of this list is hydrofluoric acid, HF. HF is an etchant, so those who are working with silicon, it can remove a layer from silicon, so it's used in photolithography. But HF is extremely dangerous. You can see the safety diamond of hydrofluoric acid here. The blue part is 4, so it's deadly. Fire is 0, so it's not flammable. And reactivity is 1, which is not so reactive. But in terms of health hazard, it is extremely dangerous. And HF, actually in low concentration, you might not even notice if you're exposed to HF because it might feel like water. High concentration of HF, it could burn, but either way, the fluoride will penetrate through the skin and it will damage soft tissues like nerve and blood. It will decalcify bone, so it's extremely dangerous. High amount could lead to death. And I always like to teach students, if you're working in a company, you're exposed to HF, what you should do. And the first thing that one should do is discarding all contaminated clothing and washing the area truly with water, and applying a cream is calcium gluconate, and seeking medical help. So we just want students to be prepared. I think the most easiest way to start teaching nanotechnology is the wet chemical synthesis approach. Maybe most of you have used this method, but I just like to review it. The wet chemical synthesis method usually uses the redox reaction, which we have a reducing agent and a salt ion solution of that materials that we want to make nanoparticle. There are some kits available. For example, Flint Scientific is a company that prepares some of these kits. One of them is a super easy kit to use, is a ruby red colloid gold nanotechnology kit. I put the link in the handout, so if someone is interested, they can take a look at this kit. The price is, I think, it's not expensive at all. So the good thing about this kit is that all reagents are normal. The reducing agent that is used in this kit is sodium citrate, which is a completely normal material. It's not dangerous at all. And even if you don't have a fume hood, you can do this experiment on a benchtop. So I think it's suitable for high school curriculum and also college curriculum. Another interesting thing is that because noble metal nanoparticles, for example, gold and silver, and some metal nanoparticles, they have enhanced optical properties, we can see a color change, and we can use simple UV visible characterization to kind of detect that color. In the case of gold is ruby red. So it's interesting to see that color change and do a UV visible characterization. And even if you just have a laser pointer, here you can see the Tyndall effect and kind of confirm that you have nanoparticles. Another kit is magnetic iron oxide nanoparticle. I think is a suitable, very easy to use kit. Is suitable for high school and also college curriculum. At the end, when you follow the instructions, you get a black magnetic nanoparticle solution. And it's very fun and interesting for students to kind of work and play with these magnetic nanoparticles. They can apply an external magnetic field to kind of collect these particles, disperse them in a solution. And at the end, they can use some surfactants. A surfactant will allow these nanoparticles to disperse. And they can try to make spikes, which I think is interesting. And they can do some UV vis characterization, see the wavelength, and do some scanning electron microscopy imaging. The price of this kit, I think, is really cheap. I put the link in the handout, so if you're interested, you can just take a look and just download the instructions. And I think it's super easy to use, and also it's fun. Actually, magnetic nanoparticles, they are the most commonly used commercial nanoparticles. They have huge application. They are used in electronic devices, in biomedical engineering, in filtration, water filtration. So it's always good to teach students how to make these nanoparticles and show what are the applications. The good thing is that this reducing method approach can easily get adopted to produce other nanoparticles. Whatever particle you want to make, for example, silver nanoparticle, zinc nanoparticle, the idea is we have a reducing agent that is donating electrons, and we have a salt ion solution of that particle. For example, for silver is silver nitrate, for zinc is zinc sulfate, and copper also is copper sulfate. So you just need to have all these reagents, and it's like a recipe, add this to that, and at the end, you get a color, you can do some characterization. But for not all of these particles, we don't have a kit available. For example, Flint Scientific only has like 2 or 3 kits that are for making nanoparticles. And if you want to make like these structures and you cannot find a kit for that, so one approach would be using a simple textbook that has done a lab work and you can follow the instructions. Also, another thing is that you can search for research journal articles and choose ones that have used a simple approach for making, for example, silver nanoparticles, and kind of reviewing the methods section and purchasing all those materials and following the experimental section on how to make that particle. It might be more complicated than using a kit. You have to like do try and error, make this solution in the desired concentration. But once you have established the process, you can use it multiple times. And another thing is that we can make other morphologies, like for example, you can make spherical particles, we can make rod structures, also even prism structures. As you see in this image, all of these solutions are gold nanostructures, but as we move from the left to right, we are having more rod-shaped structures. So at the beginning, we have a more spherical nanoparticle, and as we are moving forward, we have like a more rod-shaped structure. And at the beginning, the color is like pink or red, and we have green. It turns into yellow, orange, and then finally brown. And the brown one is the one that we have completely rod-shaped structure with increased aspect ratio. So the thing is, there's a science behind this color change, and nanoparticles, depending on their morphology and size, they react differently with light. So I think it's interesting to see this color change and also know that why this color change is happening. Another interesting experiment that I have done, and is really easy to adopt in curriculum, is making silver nanoprisms. So I found this article in Journal of Chemical Education, which this journal has some very good articles on how to use a simple lab work. Is easy to follow. This article I think was very interesting. It was very easy to do the experiment and the results were interesting. I actually have this article. If someone is interested, you can email me and I can just send the PDF article. But in this article, the authors have used a method. They have mixed oxidizing reagents and reducing reagents. And the interesting thing is that the reducing reagent, this wants to make like more spherical particles, but the oxidizing reagent wants to make like rod-shaped structures. And the combination of these two makes a prism structure. So in this experiment, once you start doing the experiment, at some point you add the sodium borohydride, and you have a very quick color change through this experiment. Just in 3-4 minutes, the color is changing from like yellow to brown and then blue. And the blue color means that you actually have silver nanoprisms, because the silver nanoparticle is mostly black in color. So it's interesting for students to see this color change, sudden color change, and they can do some UV visible characterization, like you see here, get some data about the wavelength, absorbance, compare it to a spherical nanoparticle, and then do some SEM imaging. And then we can teach them what is the application of silver nanoparticles. They have huge application. They are antibacterial nanoparticles and so on. Another experiment that I think is easy is the biological synthesis of silver nanoparticles. And the idea is we can use nature actually to produce some nanoparticles. And the idea is many plant and leaf extract, they do have antioxidant. They're enriched in antioxidant. And these materials, they can act as a natural reducing agent. Instead of like using chemicals, we can use a natural reducing agent that is in plants. So we can ask students to collect some plant and leaf extract that we know they are enriched in antioxidant. For example, collecting some green tea leaves and aloe vera, and they can just simply make an extract from these plants. And at the end, they just need to add some silver nitrate and get that black color, which we know that this black color is indicating silver nanoparticles. And even if you just have a laser pointer, you can see the Tyndall effect and kind of confirm that you have nanoparticles. So it's a very easy lab work to do in high school curriculum and also in college curriculum. I wanted to introduce a textbook. Is a laboratory course in nanoscience and nanotechnology. I think this is a super easy, user-friendly book to study. At the beginning of this book, there are some like introduction, how to characterize structure, everything about nanotechnology. And at the end of this book, we have like 12 or 13 lab work models that I think are very easy to follow. And what I like about this book that in each model, everything is explained, like what is the aim, what materials you need to purchase, in which concentration, and even comparing different methods and asking some questions. So I put the full information of this book in the handout. You can just take a look if you like, purchase it. In the previous years, when we had our workshop, at the end of our workshop, we would give away like kits and textbook so educators could use them in their curriculum. And for future workshops, we will provide this textbook together with those two kits that I mentioned, the gold kit and the Floyd kit, which I think they're very easy to use. Another instrument that I like to explain is the electrospinning. We have the electrospinning in our lab, the same exact model. I put the picture here. So electrospinning is an instrument to synthesize nanofibers, nano and microfibers. And how it works, it actually has a voltage supplier and a syringe driver, and we have a collector here. So how it works, an electrical charge is induced to a solution, droplet of solution, and that droplet of polymer becomes extremely electrified. And it will, as you see in this picture, it will create a Taylor cone because the droplet is deforming because of that voltage, high voltage. And the voltage is around 20 kV. And once the voltage reaches a critical value, a stream of jet that is made out of micro and nanofibers are going to be ejected from the needle, and it's going to be deposited on the substrate. And the substrate should be like a metal support. And the final result that you see a mix of micro and nanofibers. And if you do a scanning electron microscopy image, you can see a kind of 3D scaffold that has micro and nanofibers. So I think this is a very interesting experiment to produce micro and nanofibers and do some characterization. And we can also teach students what are the application of these micro and nanofibers. The electrospinning application, they actually have a huge application. They're used in filtration membranes because, as you see, this scaffold, they have pores. So they can exclude macromolecules. So they can be used as an additional coating on top of filters. So they are filters. They can be used in textile industry. And most importantly, they're used in biomedical engineering. And in this field, we can do a lot of fun research projects using micro and nanofibers. And the idea is in tissue engineering, we want to substitute a damaged tissue with a cell tissue that we have prepared outside human body. And we have to find a scaffold that is kind of mimicking the function and behavior of our human body. And this scaffold, because they are very similar to ECM structures, extracellular matrix, they can provide that cell support. So they are ideal candidate for cell culturing and tissue engineering applications. So just to give you an example of a research project that we can do using electrospinning, we can ask students to develop a three-dimensional scaffold from a biomaterial, in this case is collagen, for cell culturing purposes. And the idea is the first step would be students would try to make a fiber out of collagen. The reason is not all materials, they are not electrospinnable. And in order for a material to be electrospinnable, first it should be viscous. For example, water cannot be electrospun, it's not viscous. And it shouldn't be highly polar, because if it's highly polar, the surface tension of those molecules will not allow producing those stream jet of fibers. So the first step would be asking students to produce a scaffold from collagen, and they can modify the parameters, kind of work with conditions, add polymers that are viscous, and try to make a scaffold from collagen that has a good shape and morphology. And the next step, if you have cell culture facilities, you can use this scaffold for cell culturing, but I know that cell culturing facilities, they are extremely expensive. And the cell culturing technique is also complicated. It needs aseptic techniques. And if you do it wrong, the cells will just get contaminated. So mostly graduate students, they work with cell culturing. But what we can do, for example, what we have done, we have a collaborator at SWERI and also at UTSA, they have cell culturing facilities. So we provide the scaffold to them and we ask them so they can use this scaffold in the cell culture and give us some data, how this scaffold is working. So overall, I think this is a very fun research project using electrospinning. For characterization, we do have a lot of instrumentation. We have a zeta potential sizer is used for measuring the size distribution of nanoparticles that are suspended in a solution. So if you have a zeta sizer, whatever nanoparticles you make in a solution, the first characterization could be, let's see what is the size of these particles. And that could be a very easy experiment. The UV visible spectrophotometer, which actually is very common spectrophotometer, is found in many chemical labs. The FTIR that we use it for component analysis, it uses IR irradiation. And what I usually do with the FTIR, I give students some samples, powder samples that are known, for example, polymers. And I ask them to analyze these samples with FTIR, get the graphs and know what are the peaks in the graph and colorate the peaks to the specific functional group. So they can kind of guess what functional group is present in this powder material. We have X-ray diffraction, which is for crystal structure. We have a scanning electron microscopy, which is used for imaging. The one that we have in our lab is very tabletop user-friendly microscope, but the resolution is not so high because the vacuum is low and acceleration energy goes, I think, up to 15,000 kilovolts. So the resolution is not so high. But I think it's a very easy SCM to start teaching how to work with SCM, how to mount the samples, how to create that vacuum, and how to work with the software. It's very easy to use. Another instrument that I wanted to briefly explain is the Quartz crystal microbalance. And this instrument is used for thin film characterization, and we can get a lot of data with QCM. And it's not a very common or popular instrument, but it's an extremely useful one. So I just wanted to briefly describe the QCM. A quartz crystal microbalance is an instrument that measures mass per unit area by measuring the change in the frequency of a quartz crystal resonator. So this is actually the one that we have in our lab. I purchased it through Stanford Research University website. I think I've put the link of the website in the handout, and if someone is interested, they can just check the links. The price is not so expensive, so if you have some small funds in your program, this I think would be a good choice. And in this instrument, we have a sample holder and we have some quartz sensors. So the instrument actually comes with a pack of these sensors, and once you have used them, you can just purchase another set of these quartz. And how it works is that these quartz are coated with a layer of gold and also a layer of piezoelectric quartz. And this quartz has piezoelectric properties, meaning that once you apply an electrical field to this quartz, it will create a resonance frequency. And this resonance frequency is extremely sensitive to small amounts of mass and also thickness. So it's used for thin film characterization. If you have a layer on top of this quartz sensor, then the resonance frequency is going to change. This device is going to record the frequency change, and you can kindly do some calculation of what is the mass and what is thickness. So this is how it works. So as I mentioned, the quartz crystal microbalance works with a piezoelectric quartz, which is the sensor part of this instrument. And you see in these two pictures, this is showing the quartz gold-coated crystal, which we are applying a voltage to this crystal. It will create a vibration at a specific frequency, and this vibration is going to change once you have an additional layer. And you see in this left picture, we have added a layer, which in this case is just a sample of antibodies. And once you have this layer on top of the quartz, the frequency that is getting recorded is going to change. And how you can correlate frequency is with the Sauer-Bray equation. You can see the equation here. Frequency relates to mass, but they have opposite relation. If the frequency is decreasing, means that you actually have a mass on your quartz. If the frequency is increasing, means that you are removing a layer from your quartz. And C is a constant value that is dependent on the quartz properties. So with the advanced QCM versions, they are more expensive. They give you a graph and they kind of use this equation to kind of, they give you the final delta M, they give you the final thickness, but with the simple version of QCM that we have in our lab, the instrument just records the frequency. And you have to use this equation to find the mass and find thickness. And I think this is very good for students. They get to do some characterization and they get to analyze those data and finally make some graphs. So the graph that we can get with QCM is frequency versus time, frequency versus number of layers, and also mass versus time, mass versus number of layers. You can see in this picture, again, we have a layer. We have a quartz that has not been deposited by any layer. In the first step, we have one layer absorbed on top of this quartz sensor. So the frequency is actually decreasing. It becomes constant in a specific area, which we have no more materials absorbing. Then we have a washing step. We add another layer, and then we have again frequency change. So at the end, the point is kind of drawing these graphs, analyzing all the data, and getting the frequency and mass graphs. We can do some fun research projects using QCM. And I'm just giving you an example. We can make a high sensitive biosensor with QCM for detecting molecules. A biosensor is usually made out of 3 elements. One of them is the sensing element, which in this case is going to be the QCM. The QCM is actually recording mass and recording frequency. And as you see in this picture, we have a layer, a biorecognition molecule, which in this case is antibodies. And the second part is actually the analyte, which is in this case is antigens. So what we can do, the purpose could be making a biosensor that we want to use an antibody, and we want to use the QCM to kind of increase the sensitivity of this sensor in detecting the analyte. So the whole purpose is detecting this analyte, even if we have this molecule in a nanogram concentration. And the project could be the first step. We can ask students to deposit or absorb a layer of these molecules, for example, antibodies on the QCM sensor. And then we can ask them to use this sensor to detect this antigen. We can give them antigen samples, use this QCM that they have developed to detect how much analyte we have in a sample solution. And this could be a very good experiment. They can analyze their data and they can compare it with already available sensors and kind of compare if this sensor is highly sensitive or not. Overall, I think is a very fun research project. We can have a lot of data using QCM. Another experiment that we can do, we can not only have like a single layer, but we can have like multi-layers and characterize each of these layers with QCM. So it does have a lot of application in drug delivery and so on. I'm just going to briefly explain that we have like polymers with opposite charge that we can absorb these polymers on top of each other. and kind of detect what is the mass and thickness of each of these layers. And this is also good for experimental research, and it does have a lot of application in sensors and also drug delivery. One thing that a very good advantage of our program is that we have training, which is done at UTSA. There's a center called Kleberg Advanced Microscopy Center. And this center, they have the most state-of-art spectroscopy and microscopy instrumentation. They have about like over $5 or $6 million investment in infrastructure. So it's a great institute, and they provide service to different areas. They provide service to research faculties, training, industry, and also they have an outreach program which is focused on community colleges and also K-12. So the idea is teaching community college and students on how to operate and work with this instrumentation. I think overall, this microscopy center training has been a great opportunity for our program. A microscope that they have is a transmission electron microscope. This is a high resolution electron microscope that the resolution goes up to, I think, 0.4 nanometers and even less. So if everything goes well and you have a very good image, you can actually see individual atoms in a nanoparticle. And I think this is super interesting for students to see these atoms. So you see in this picture, our students are working with the transmission electron microscopy. The training that is provided with this TEM is how to mount the grid on the sample holder, which you see is here, how to insert this sample holder in the vacuum chamber without breaking the vacuum, how to work with these knobs, how to adjust all the parameters, how to work with the fluorescence screen, and how to work with the software. So in each of these microscope session is about like 4 or 5 hours. The first 2 hours is demonstration, and the next 2 hours students can work individually with these instruments. So because they're working individually, there's a limitation in numbers. For each session, we have about 5 or 6 participants. We are planning on having this electron microscope training in our workshop and kind of having some sessions of this microscope included in our nanotechnology workshops. You see in this picture, our students are working with TM. They're quite happy about it. Another instrument is atomic force microscopy. The AFM is probably the most popular instrument in nanotechnology. It can provide many data, like you can do force characterization. You can analyze samples that are liquid, like biological samples, and you actually don't want to dry those samples because you don't want to damage them. You can get data such as height, imaging, and 3D pictures of a sample, which is very interesting. The training that is done with atomic force microscopy is first how to mount the cantilever on the sample holder, which is a sensitive approach because the cantilever has a very thin tip, and students have to use tweezer to kind of grab that cantilever. And if the cantilever drops, so the chip will actually break. So what they do is students will practice with a broken cantilever, and kind of when they have practiced a lot, they can use actually a cantilever with the tip and put it on the sample holder. And the other training is aligning the beam, doing the approach step, and also working with the software, and finally getting some images. And all students, they get to work individually, each of these steps, and finally get an image from AFM. Another instrument is the X-ray diffractometer. This X-ray diffractometer is actually a multi-purpose X-ray machine. The one that we have in our lab is a very simple version, but this one can analyze powders, it can analyze liquid, it can also analyze thin films. So it's a very multi-purpose X-ray machine. And the training that comes with this X-ray machine is students, again, They get to put some powder samples on the sample holder. They would align the beams and they would work with the software. Another instrument is the field emission scanning electron microscopy, which we have done the most training with this FESCM. It's a great instrument to work with, and it will get a resolution of 0.4 nanometer at 30 kV. It's actually very similar to the resolution of TEM. Also, it can give some component analysis. So the training that comes with this field emission scanning electron microscopy, the students, again, they will work with the sample holder, mount some samples, and they get to insert the sample holder in the vacuum chamber without breaking the vacuum. And then they will work with the software, adjusting stigmatism and making a high resolution image. And at the end, they will do some component analysis using the EDAX software. Another lab work that I wanted to introduce is a self-assembly. I think self-assembly is a very important concept in nanotechnology. And the reason is in nature, we have a lot of self-assembling biomolecules. For example, DNA and protein, they're all natural self-assembling molecules. And most of the times, what we're doing in nanotechnology is we're trying to mimic the behavior of these self-assembled biomolecules and make a handmade structure. This is a spontaneous process where atoms and molecules are organizing themselves into ordered structures. They use electrostatic interaction, hydrogen bonding, and a lot of these forces to kind of make an ordered structure. What I have done in my lab work, I have used a natural molecule, which is a dipeptide. This is a molecule that has hydrophobic groups, and once it's dispersed in a solvent, it can create micro nanofibers just by any external force. Just you have to purchase this dipeptide, mix it with the appropriate solvent, and once you put a drop of this solvent on a substrate, you can see that there, once the solvent evaporates, once you do a scanning electron microscopy imaging, you can see these macro nanofibers. So it's very interesting. Without any additional force, these natural molecules are making macro nanofibers. So hopefully we will be able to cover the self-assembly concept in our workshop. In the previous years, we have had nanotechnology workshops in collaboration of nanotechnology centers. The NAC Center has greatly contributed in organizing these workshops. Bob Erman and his team, Dr. Kakmak, they have done a great job in organizing these workshops. We have had them in 3 years, and each year the NAC Center was the main organizer, but we also had presenters coming from other nanotechnology centers presenting two of the 1 week session workshop. We have had presenters coming from NanoLink, MAD-EDU, and also the Support Center for Microsystem Education. Overall, it has been a great experience for our program. These nanotechnology workshops, they were for high school teachers and high school students. So it was a 1 week workshop. The first 2 days, we had parallel sessions. Students will work with one group, teachers would work with the other group. And in the next days, they would switch, and we had like a combination groups, which we had breakout session, like a rain session. We had FTIR analysis, scanning electron microscopy analysis. We did a self-assembly lab work. So overall, it has been a great experience for our program. We get to recruit more students with this workshop. And also we got in contact with high school teachers, and they were able to include some of those nanocurriculums in their courses. And that is actually a very good way to increase the knowledge in the community about nanotechnology. In our future nanotechnology workshops, we are planning to integrate some engineering components in this workshop. So the idea was collaborating with the engineering department at MVC and using our 3D printers to actually print some hands exoskeleton. And one day students could print those. The other day they could do assembly and function and kind of use that hands for specific purposes. And we are planning to have parallel macro and nano biolab experiments. And hopefully we are able to cover some of those experiments that I just mentioned. And hopefully we can see some of you in our next year workshop if the campuses are reopened and we actually get to organize these workshops. So I'm just going to end my presentation here and open it for questions and discussions. And we also have a poll question that Billy is going to bring up.
All right, thanks, Neda. Maybe first we can do the poll question, Billy.
Sure. Yep. So we have a poll question. It says, are you interested in applying the micro nanobio project research discussed in this presentation in your current curriculum? Yes, no, or does not apply. Don't forget to hit submit when you select your response. Give you guys a couple more seconds to respond and then we'll end the polling. All right. So we had 47% of those who responded said that yes, they are interested, and there was 53% who said does not apply, but nobody said no. So nice job, Neda.
Thank you. Not a bad result.
No, that was great.
So any question?
So I think there's some in the chat. I know Mike Losecki said that this would be a really fascinating webinar for you to kind of talk about the quartz crystal microbalances. So you might be getting a webinar invitation pretty soon from Mike.
So
Actually, it'll probably come from Bob.
Oh, it'll come from Bob. So Bob's question was, who will the workshops be targeted for?
So last year's we targeted high school teachers and high school educators, but this year we are definitely targeting college faculties as well. But again, high school teachers are going to be important for these workshops because they are our main connections with high school students that they want to choose these programs and enter nanotechnology workforce.
And how long would the workshops be?
So in the past we had 1 week. We are planning to have the same 1 week, but if we can incorporate some microscopy trainings, it would be longer, like maybe 2 weeks.
Cool. What aspects of the program do you feel would engage women students the most?
So I found it interesting that women are very interested in biomedical engineering research projects. So the cell culturing, the biomedical engineering projects, they're really interested to participate. So I think having more of these research projects compared to like material research project, we can engage women more. This is my idea.
Oh, cool. Then Oscar asked, do the students also see the TEM sample preparations or even any sample preparations?
So it's a good question. Most of the times the sample is prepared by UTSA and they just give us a prepared sample. But for TEM, for nanoparticles, it's just a droplet solution that you put on a grid and you just wait until it dries. This is for TEM. For SCM, for FESCM, the sample that they have provided is a tiny little silicone support that they have like deposited or absorbed structures on them. It could be like a gold nanoparticle, or last year we had some carbon nanotubes. So they were provided by UTSA, but we can always bring our samples. The thing is that we have to put them in a tiny silicone that will fit in the sample folder.
Cool. So Jim Smith has asked, have you had your students compare the antibody QCM results with bilayer interferometry of SPR antibinding binding techniques? I don't even know what interferometry is, so that would be an awesome thing to,
That's very
explain.
interesting. No, we haven't.
Okay. Oh man.
That would be very interesting.
Yeah, it sounds really interesting, I think.
Well,
SPR antibody binding techniques.
Yeah, Jim, you gonna say something?
I was just going to say, I have access to surface plasmon resonance image techniques to analyze antibody binding, and it's often used in industry.
That's a great idea.
Yeah, it'd be fun. It'd fun to compare. They could send samples, and we could run results and compare them, and they could kind of get a feel for the different types of instruments used to do binding kinetic studies.
So do you know what is the sensitivity of detecting antibodies using your technique, the SPR antibody binding techniques?
Yeah, very, very sensitive, picomolar or whatever.
Oh,
yeah,
that's good. I know QCM can detect in like nanograms, so that would be good comparison.
Yeah, I think it'd be fun to do sometime. So
what exactly is QCM and SPR for, say, the idiots in the room like me?
So she explained the QCM, right? The quartz crystal microbalance, where basically you get a shift in frequency as mass adds to the surface. SPR, you shine a laser off the back side of the gold surface, and there's an evanescent wave that is generated out into the solution about 50 nanometers close to the surface. And as mass adds to that, it basically changes the absorption frequency of that SPR due to surface plasmon resonance being generated. And so you're able to, by measuring these very sensitive shifts in frequency, you're able to come up with nanogram measurements like she talked about of things adding to the surface. And you do it in real time, so then you can back out what the kinetics are of your antibodies sticking to your antigens on the surface, which is very important for drug development companies, because they want to know what sticks to certain receptors that they harvest from the body, indicative of certain types of diseases. And then they can refine those molecules to develop antibody therapies like Humira, which you see in practically every commercial break, I think, in the United States. So.
Yeah. Oh, cool. Surface plasmon resonance. I've heard that.
Do you have videos about QCM? I don't have videos, but I can always do a YouTube search and see what are good videos. And if someone has used the exact model that we have, I can send you some YouTube videos if I found them.
Yeah, cool. And then Dev asked, any measurements for physical properties of the nanofiber scaffolds, like stress versus strain, electrically neutral, hydrophobic, philic?
That's a very good question. So far, we have only done scanning electron microscopy imaging to see the morphology, but this could be also interesting. I don't know exactly how to measure the properties, mechanical properties of this fiber. Maybe we can use AFM. And the hydrophobicity and hydrophilicity, we haven't done it, but I think it depends on what components you're using to make that scaffold and what is the solvent. Is it like hydrophobic or hydrophilic? And but we haven't done these measurements.
don't know, Eric, what kind of link were you wanting to get? I see that there's, give me a link I can send to our bioscience faculty. We're gonna have the presentation sent out. All right. How about, did you have any idea about Open QCM and its applications? I don't know what QCM
so
is.
what do you exactly mean about Open QCM? Do you mean like a QCM that works in liquid?
Down below, he says Open QCM is open.
No, open QCM it means that it's free and it's compatible with Arduino.
Okay, so it's free and just open to the community. So I guess it's just kind of open source QCM.
Do you have a link or website that I can check?
Yes, it's OpenQCM.com.
Oh, great.
So just go and you will get the website.
So what kind of information is included?
Oh, there it is. Peter kind of put one in the
Oh.
link. Cool, thanks, Peter. All right, a couple more questions. So one question, are the workshops open to internationals or are they reserved to national teachers, students?
I would say national. We haven't had international participants.
Already NASA uses OpenQCM for satellite projects.
Yeah, I don't know. We'd have to talk with about international. I honestly don't know the answer to that. And then maybe one more question. Anyone else have any last questions before we end? No. All right. Well, thanks everybody for coming, and thanks again, Neda, for giving the talk. It was really fast. I learned a lot about what you have to offer at Northwest Vista College, and I'm looking forward next summer that we'll have workshops. You know, keep our fingers crossed that we'll be able to get people face to face to participate in the workshops.
Sure.
Next week, Brandon Rodriguez is going to be giving presentations on NASA education and micro nanotechnology. So we'll look forward next week to hear from Brandon. All right, everybody have a great rest of the week.
Thank you.